Hey guys, welcome to today's video on Thevenin's theorem. In electrical engineering, we often encounter complex circuits which become tedious to analyse. Thevenin's theorem provides an elegant solution to this problem through circuit simplification. By utilising this theorem, circuit analysis becomes more efficient and easier to comprehend. So without further ado, let's dive in. Thevenin's theorem states that any linear bilateral circuit can be replaced with an equivalent circuit consisting of a single voltage source in series with a single resistor. This equivalent is known as the Thevenin equivalent circuit and allows for the simplification of circuit analysis whilst preserving the electrical behaviour of the original circuit. There are two key components within the equivalent, the Thevenin voltage and the Thevenin resistance. The Thevenin voltage represents the open circuit voltage measured across the terminals where the load is connected. The Thevenin resistance, on the other hand, is the equivalent resistance of the entire network as viewed from the same terminals, with all voltage sources replaced by short circuits and all current sources replaced by open circuits. Together, these two values form the complete Thevenin model. To determine the Thevenin equivalent, we first identify the two terminals we wish to analyse. Secondly, deactivate all independent sources respectively and determine the resistance as seen from the open terminals. After this, reapply the sources and calculate the open circuit voltage. Once both values are known, create the simplified equivalent circuit with the load resistor and complete any further analysis required. Let's try an example. Here we have a simple DC network. We'll determine the Thevenin equivalent voltage and resistance as seen across the 400 ohm load and then use those values to calculate the voltage and current through it. To begin, we find the Thevenin resistance. First, we deactivate the 12 volt source by replacing it with a short circuit. Next, looking from the terminals into the circuit, we see the parallel sum of the 100 and 200 ohm resistors and the series addition of the 300 ohm resistor. This equates to a total of 366.67 ohms and therefore is our Thevenin resistance. Now we determine the open circuit voltage across its terminals. Due to the open circuit, the current from the battery only flows through the 100 and 200 ohm resistors. Hence, the Thevenin voltage in this scenario is equivalent to the voltage across the 200 ohm resistor. After calculating total current, we can use Ohm's law or simply the voltage divider rule in this scenario to find our Thevenin voltage, which equates to be 8 volts. We can now construct the Thevenin equivalent circuit as seen below. Now, utilising Ohm's law, we can find the load current to be 10.44 milliamps and the voltage across the load to be 4.17 volts. This answer matches perfectly against the original network and hence demonstrates the simplified analysis Thevenin's theorem provides. However, despite its usefulness, it has its limitations. Thevenin's theorem only applies to linear circuits, meaning those that obey Ohm's and Kirchhoff's laws. It doesn't fully capture internal power losses and becomes frequency dependent when applied to AC circuits with reactance. Overall, Thevenin's theorem offers an elegant solution to simply analyse electrical circuits by reducing the complexity to evaluate internal network behaviours. That's all for today. Come back next time.